Older electric vehicles are often powered by DC series motors, the same kind of electric motor that is on my DIY electric bicycle. The nice thing about this kind of motor is that it can run on DC electricity, so it can be powered directly by a bunch of batteries, and it can develop copious amounts of torque when it gets turned on, making it very suitable for driving some sort of heavy vehicle to provide good acceleration. However, this type of motor also has drawbacks. It's not very efficient, and it requires quite a bit of maintenance. That's why in modern electric vehicles, so modern electric trains and cars, asynchronous AC motors are much more popular. In order to understand the asynchronous AC motor, let's first take a look at the normal synchronous electric motor. So here's a schematic drawing of a synchronous AC motor. So as you can see, what we've got is 3 coils that are set up in sort of a triangle arrangement, each 120 degrees apart, and they're surrounding a magnet. And this magnet is on a shaft that can rotate. Now what we do is we connect these 3 coils to 3 separate AC power supplies, 3 separate phases of AC power. The nice thing about these is that these phases are also electrically 120 degrees apart. So the coils are physically 120 degrees apart, but the phases of electricity that we feed into them are also 120 degrees apart. And that means that when we turn on this motor, what we're essentially doing is creating a rotating magnetic field using these 3 coils. So every one of the coils gets AC power, but they're all 120 degrees apart, meaning we get effectively a rotating magnetic field. And that rotating magnetic field makes the permanent magnet that is in the center rotate. And that's how this motor rotates. The reason it's called a synchronous AC motor is because the rotational speed of that magnet is equal to the rotational speed of the rotating field. Right, that makes sense. The problem with this kind of motor is that it uses a permanent magnet or multiple permanent magnets, and permanent magnets can be expensive, especially as they get bigger and need to be very, very strong. That's why we also have asynchronous AC motors, which are AC motors that don't use a permanent magnet. Instead, they use a metal cage. So you might be wondering, how on earth does that work? How does a metal cage rotate? It's not magnetic, right? How is it going to be affected by this rotating magnetic field? As you may or may not remember, if we have a moving magnetic field near some sort of conducting material, that magnetic field will induce an electric current inside that conducting material. So in this case, the rotating magnetic field created by our 3 coils will create electric currents inside that metal cage, because it conducts, of course. And those electric currents will create a new magnetic field around that cage, because when an electric current runs through a conductor, it also creates a new magnetic field. So now, essentially the cage has become magnetic. We've made it a magnet by inducing currents in it, and now it starts rotating just like the permanent magnet in the synchronous motor. But there is something very, very interesting about this. You see, the speed at which the cage rotates is never exactly the same as the speed at which the field rotates. So why would that be? Well, you see, if the cage has exactly the same speed as the magnetic field, so there is no speed difference between them, then effectively the magnetic field is stationary. If you compare it to the cage, it's effectively a stationary field. And a stationary field, well, that doesn't create any electric current. So if the speed of the rotating cage is the same as that of the magnetic field, the motor loses all of its torque, and it's no longer a motor. Therefore, in this type of motor, the cage, the rotor, always spins slightly slower than the rotating field, and that's why it's called an asynchronous electric motor. The difference in speed between the rotor and the rotating field is called slip, and it can be calculated using this formula, which says that slip is equal to the rotational speed of the field minus the rotational speed of the rotor divided by the rotational speed of the field. If the rotor is stationary but the field is rotating, the slip is equal to 1. If the rotor has the same speed as the field, the slip is equal to 0 and the motor has no torque at all. But there can also be some very interesting situation. What if the rotor is forced by some external force to go faster than the field? Okay, so say we have a vehicle, okay, and the rotor is connected to the wheels, and we accelerate the vehicle to 100 kilometers an hour, and then we deliberately make the field rotate very slowly by adjusting our power supply. But of course the rotor just keeps going because we're in a car that's moving fast. What's happening then is, if you work out the formula we just discussed, you see that we get a negative slip. And a negative slip means that the motor is now generating power. So that means we're now using effectively regenerative braking. We're generating electricity using the motor, and we're also slowing down the vehicle because that negative slip doesn't want to be negative, right? It wants to be a positive slip. So the vehicle is going to slow down, the rotor is going to slow down to match the speed again, or to go below the speed of that magnetic field. And so that's how it's possible to do regenerative braking even if there are no permanent magnets inside a motor, and that's pretty fascinating, right? The reason this type of motor is so great is because it's just a steel cage running on some bearings, right? There are no brushes involved, no commutators, no components that wear out. It's just a shaft that is rotating in free air, which makes this motor very efficient because there is little to no friction and means there is very little maintenance that has to be done. At the same time, the motor can develop large amounts of torque because we're not using permanent magnets, but we're using electric currents in a metal cage, which we can make as large as we want, right? As large as the motor design allows for. So there you go. That's what an asynchronous electric motor is. I hope you've enjoyed this video, and of course, thank you for watching.